Holding. Okay, welcome back. So that's yesterday we introduced several important things, right? Let me take a look. Let me give you really brief recap. Okay, yesterday we talked about how we determine the function of a sigma mix of a material. Right, you can see that the sigma mix, we can obtain that by using m moment divided by the sectional moduli Sx. Okay, and then you can see this is the function of the material, stress function of the material, normal stress function of the material. Okay, and then you can use this function to determine wherever you want, okay, the stress at everywhere you want in this material. And then we introduced a really important concept of that, how to determine the shear stress in the section. Okay, so how do we determine that shear stress? We were using the horizontal shear stress, because horizontal shear stress is easier for us to do the force balance. Okay, and so that's why we want to use the horizontal. We need to cut it. So when we cut it, we will left upper part. Okay, the upper part. And after to do the upper part, we can see the left-hand side and right-hand side has the stress, normal stress due to the moment, right? So left-hand side is m, the right-hand side is m plus dm. Okay, so there are three forces. The force, of course, is come from stress times the area. Okay, so after that, we done that, and then we conclude that, oh, the tau here is V divided by VQ divided by IB, or VQ divided by IB. What is Q? Q is actually the distribution of the area respective to the axis. Okay, the axis, the neutral axis. But we don't need to do the integration all the time, because it's easier for us just using a proper, centroid distance of that area and times its own area, and then we can get the Q here. All right, so that's it. And then we found that the VQ divided by IB is kind of parabola. Okay, it's a parabola, which means that it's a second order polynomial. And you can see that at the top and bottom, it is shear stress free. Okay, shear stress free. And the shear stress has its maxima at the neutral axis, right? Then we need to give you some limitation, because our proof based on the section that we choose. We choose rectangle, right? Rectangular section. So it won't fit to triangle shape or circle shape. Only if you focus on the neutral axis for the circle shape, because you see, luckily, you can see that this shear is kind of has a boundary parallel to that, to y, parallel to the y. Okay, so that's how, that's why this line is satisfy the condition that we prove in the rectangle shape. And then we talk about how it distort in the shear. Okay, so the shear strength in the middle, in the neutral axis, it will looks like a shape like this. Element shear stress will make the stress element twisted like this, but at the top or bottom, it will remain the same. Okay, because there's no shear stress at the top and bottom. And then we give you some problem solving steps. Draw the shear force and bending moment diagram and calculate the centroid neutral axis and calculate the first and second moment of the section and then calculate the normal stress and shear stress. All right, so this is the typical classic example. Okay, so after we done this, we draw the first step, we draw the shear moment diagram, and we know that the C points has the value like this. Okay, and then we have the I here, easy because this is a rectangle. We just substitute the value, easy, and sigma C minus my divided by I, and you can get minus 26.9 MPa. And you see that, okay, this is positive M, so it is compression at C point. Oh, by the way, did you see that this is 75 and this is 25? Okay, because 75 is from the bottom, right? 75 to the 75. So you need to minus 50. Okay, otherwise you will make it wrong. All right. So 75 from the z-axis, you will off the chart, off the exceed the top ceiling, right? So be careful about this 25. Okay, so that's it. Now let's continue to next page. All right. Next page, we are going to the continue. Okay, continue. Okay. So previously it said we need to determine sigma C. Okay, we've done that. But tau C, we haven't done it yet, right? So what is tau C? Tau C, we need to determine AC and YC and QC. So what are they? AC, YC, QC. Okay. So the let me take a look. Sorry, should be green, right? Green. Okay. Green. Okay. This is the shaded area. Okay. So the shaded area, AC is what? 25. Okay. And what is YC? YC is 25 divided by 2 plus 25. Okay. So not difficult, right? 25 times 25, 625 millimeter square. YC is 37.5 millimeter. QC is AC YC equal to 23440 millimeter 3. So the tau C equal to VC QC divided by IB, which is equal to okay, 8400 times 23440. This is minus. Okay, this is we need to focus. Be careful. Minus, where is come from? Minus 80. Minus 8.4 Kn, right? So this is minus 8400. Okay, be careful. And 2.083 times 10 to 6 times 25 equal to minus 3.8 M pop. Okay, that's it. That's it. So tau C, sigma C, we have done that. We just substitute the value, and well, you can see that as long as the cross section is okay, it's easy, like rectangle. Okay, so everything is easier. And the second question is that show the stress element. Show the stress element. Show these stress. Show these stress on the element. Okay, so C. So this is point C. Point C, we want to draw the stress element. And again, you see here. Oh, I shouldn't write it down like that. Haha, sorry. You lose a chance for the bonus. 我写太快了，我原本想要问大家方向是什么。Sorry. Okay. You see, minus 8.4 kN, right? Minus 8.4 kN. This value is actually a shear moment diagram, right? Shear moment diagram. Remember, the V is downward as the positive, so this minus 8400 is up, right? Sorry, I write down too quick, and then I should ask you a bonus. I should give you a bonus chance. Okay. And then the moment is 2.24 kN dot M positive. So it makes a happy curve. Okay, smiling curve. So now we know the direction of the 8.4, shear and moment. Okay, both we know that. So now we can draw that figure. Maybe it's too big. Okay, this is shear stress element. And of course, this is the shear stress. What is shear stress? Shear stress is 3.8 MPa. So did you see that it's a little bit weird? You see this is upper, right? Up. And your tau C is minus 3.8. But if you read, because the convention, sign convention in shear moment diagram is kind of different from our original X and Y coordinates. So you see tau C minus, suppose in the previous chapter 2, it looks like you should go downward, right? But because our value is come from shear moment diagram, so we need to be really careful that when we draw the shear stress, when we draw the stress element, we need to identify the actual direction of the force. Okay, so yeah, this is a you need to pay attention on this. So up the opposite side will be down, and you will have shear strength in pairs, in groups. So you have 4 of them. And then you have the tau, sigma C. Sigma C is Okay, that's it. So yes, a little bit difficult that you need to pay attention on the actual direction of that. 好，这边要讲一下哈，就是我们这边掏 C 算出来了啊，它是负的。OK，但是你要小心哦哈，就是这个掏 C，如果今天我们在一般的在 Chapter 2的时候，我们那时候说，哎，主角面在这里啊，好，主角面在这里，然后如果今天是负的掏 C 的话，哎，它应该是往下的，对。但是不要忘了，我们这边的 tau c 的 v 的值是从哪来的？我们的 v 是从那叫什么啊？简历弯曲图，简历弯曲图来的。简历弯曲图它的 sign convention 是跟我们其他的有点不太一样，对不对哈？我们在 sign convention 在简历弯曲图的时候，它是向下，在右边这个截面上的话是向下为正。好，那所以说这边是负的，表示它向上。所以我们真的在画这些 stress element 的时候，我们千万要注意，就是说我们要画的是真正的方向，哦，真正的方向。那所以这边就是有一点点需要去转换的哈，就是简历图跟弯曲图的简历的值的正负号是跟我们一般的有点不太一样。但我们真的在画 stress element 的时候，那当然要回到我们的原本的 Chapter 2的 sign convention。OK， 所以这边是有一点需要大家注意的。Okay, so if you can accept that, you can see that now we can determine shear stress, normal stress, every point in this material. Wow, that's powerful, right? This is really powerful, powerful formula to do that, to achieve that. We can, understand all the points of the stress, understand the stress distribution in this material. Okay, so if you can understand this, we can continue our lecture to see the circular cross-section. Circular cross-section. Circular cross-section, well, it's not, we can only determine the shear stress at the neutral axis, right? So it will be a little bit different from others. All right. Next, shear stress. Shear stress in beams of circular cross-section. So you can see that this is the circular cross-section, and only here is okay, right? Let's take a look. You can see that this boundary, just like this, they are parallel to the y, so this line is okay. But this line is not okay. Other lines, this line is not okay, right? Maybe you will ask why we cannot just say why we cannot just do this, why we cannot just write down shear stress downward. Yeah, can we actually do that? Maybe not. Maybe you can see that. Okay, so this is a stress element, not in the material. Sorry, not in the neutral axis. It's just the boundary. Okay, so you see, if you say, okay, this surface is downward, which means that it must has a what's that stress-free. This is stress-free, but your stress is come in pair, right? Come in pair. So this is not okay. So if you say there's a shears here, which means that it will come in pair, right? It's come in pair, but there's no material here. There's no material. It shows that there's no stress at this surface. So you cannot assume like this. You can only assume like this. F. Okay. So you can imagine that actually this force, this stress element, stress is actually like a water. Okay, you pour down your water and then it flow like this. Okay, so your stress element must be, if you want to determine that, you must has the oblique stress element, and then your shear stress can become impaired. Okay, otherwise you cannot find a proper stress element along the edge. Okay, but here is okay, right? Here is okay. Your shear stress, if you draw here, which means that yeah, your shear stress can come impaired. Yes， 啊，这样听得懂吗？就是说这边你的 stress element 画一个方框框在这边。如果你假设说，哎，就算这就是不在这里的地方，不在中心轴的地方，你也是画一个方块，然后假设它是就是要算垂直的。哎，可是你看啊，你的 element 写在这里，如果你垂直的话，你的 shear stress 要 come impaired，对不对？那这边是空的啊，没有啊，啊，没有这种东西，所以你这个 stress 不能 come impaired。它就是不能四组一起出现。那如果要出现的话，一定是要是这个 element 一定要是斜的，要是斜的，好，要是斜的。那可是我们的 stress element 从以前到就是之前在做推导的时候，我们是以正方形的嘛，哦，然后它是就是不是斜的。那你可以看到这边它斜的，它就可以了。这边它就可以是这边就有材料了啦，你看这边就有材料了。所以它有材料就会有 shear stress 可以成对出现。那这边也是啊，哎，这边有材料了，这边也有材料，这边也有材料，这边有材料，所以它可以成对出现。OK，所以这边 OK，这边不 OK，这边也不 OK 啊，因为我们的 element 就是如果要这边要成对出现的话，这 element 是要是斜的。那斜的话，跟我们之前在算的那个是不一样，算就是在做推导的时候是不一样的，好，所以我们算出来的公式不适合在这里。当然，你要算这里的 shear stress 当然是没有问题的，好，那要用更复杂的、更进阶的式子去算，不能像我们之前这样推导那么轻松了哈。Okay, so which means that if we want to determine the shear stress, the region apart from the neutral axis, we need more advanced solution, advanced tool to determine the shear stress. All right. But anyway, I just want you to know this is the only place that we can apply our tau equal to VQ divided by IB. Okay. And how to do that? Not that difficult. Okay. All we need to do is using this shaded area and find the centroid. Okay, the centroid. I want to know this is y bar. Y bar. Okay. So Iz equal to pi d4 64. Okay, and so which means that your IZ is pi r4 divided by 4. Okay. And then because this is a half circle, so we divide by so this is half circle pi r squared divided by 2. Okay, the half circle area. And this is y bar. Y bar, okay, y bar is 4r over 3 pi. Well, I don't remember where I get this. I guess it's from what? From calculus, I guess. Or you can Google that. Okay, so if you have the half circle, your centroid actually your centroid height will be 4r over 3 pi。还记半圆的直心，半圆的直心会是在4r 除以3拍这个高度。这个我记得好像是在哪里有学过，应该是在那个什么微积分里面有学过吧，对不对？是这样吗？还是在哪里有学过？半圆的 centroid 有记得吗？半圆的 centroid 在哪里学到的？你知道这个数字吗？不知道，哦，不知道啊。好，我记得，好，其实回到家你也可以自己试试看的哈，真正的去做积分，哦，去做积分，反正这就是直心嘛，所以我们之前有就教那 Q 啊，对不对哈？我们就直接去做积分就好了，一次举的那个除以它的面积。OK，Anyway，回去可以试试看哦，这应该用你的微积分就可以做出来了啊。好，OK。So after we done that, so I suggest that maybe you can try that back home. Your y bar of the half circle centroid coordinates. You can determine that by using calculus integration. Okay, I guess it must be, it should be okay. And then you can get this value of 2 over 3 r cubed. And b equal to 2r, right? So this is r, this is r, so 2r. So your tau max equal to blah, 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 4v divided by 3a. Okay, so yeah, that's it. So you can see that we only can determine the circular cross-section tau at the neutral axis. And neutral axis will be the tau max. Maxima shear stress. Okay. Then, if you want to do the hollow round beam, it's very similar. Okay, hollow round beam, I just the original I minus the empty part. Okay, again, so you see R1, so minus it, just all minus them, and you can get a more complicated result. And the shape of the Okay, so this is the shaded area, and this is the central. And we are going to calculate the shear stress at this. Okay. So you after you've done this, you substitute r equal to 0, you will get a solid circular beam. All right. Well, it's not really important. I just want you to know circular beam also available for our can be applied to our shear formula. 好，这边的圆形的跟中空圆形的材料其实 我是觉得没有那么重要了哈，但是就是告诉大家，就是说，这你看到圆的话，你只能算它的中心轴的东西，中心轴的简历，然后它要算的 Q 就会是上半部的上半部。那即便是这个是中空圆管，你的面积也就是这样的。然后它要怎么样去算呢？就是把原本的实心的去减掉中空的部分就好了。不管你的 I 跟你的 Q 都是这样子，OK？对，大概就是这样。然后的 B 也是B 是 R2 减 R1 乘以2，OK？Right. So, hollow round beam and circular beam. Well, it's not really important, but just let you know the concept. Really important thing for a beam is that we're going to give you I shape. I shape beam is more commonly used in the real world. So, for example, if the shear stress, distributed load, subjected to loaded on the I-shaped beam, I-shaped material, and this is the cross-section beam, right? You see Y, this is Z, okay? And you see that there's a shape like this, okay? Shape like this I. And if we want to know the shear at the level EF, and this EF is above the neutral axis Y1, okay? So this EF is where is our target. So we are going to determine the shear stress at that point, at that level, at that height, okay? So now you can see that actually, this will be our shaded area. This will be our shaded area, okay? Now, let's take a look. This is a little bit difficult, okay? Again, we said we can only determine the rectangle shape, right? So basically, this is not really rectangle because this is I shape. So actually, only this part can apply for our shear formula. This part, no. This part is because you can imagine that if your loading is here, your loading is here just like this. Your loading is here. You can imagine that this shape, the top, is called should be flanges 是 E 吗？就是这个东西叫做 E 吗？我也不知道，还是这叫做 web。Well, we only can focus on web. We cannot focus on flange. Why? Because when we do the force, you can see that it will twist it like some sort of like this, right? So actually, this is a little bit complicated. You can see that this is downward load, and also a little bit in the force is kind of travel from here to here, here to here. So actually here and there is a little bit complicated. Okay, it's not uniform stress. So you can see that in our course, in this mechanical material, we always talk about uniform shear, uniform stress, uniform shear stress. So here it's too complicated. We cannot determine that. All right. So, okay. 讲中文的哈，就是说这边你可以看到，如果今天有一个力这样子压下去的话，这个翼板它会有点这样子凹下去，对不对？那你会想想看，这个凹下去，然后你会发现这个力其实好像是有点这样子，就是从这边流动过，流动到下来的，流动下来，所以这边是又有往下的力，又有往内的力，哦，所以实际这是非常复杂的，所以上下板是非常非常复杂。可是，在我们的财力里面呢，我们都在着重在均部的，对不对？就是很 uniform 均部的stress，不管是剪切应力也好，还是 normal stress 也好，它都是要很均匀的，我们才会嘛，对不对哈？所以这边我们就不会了，那不会了，我们就不能算了哈。所以说这边其实根本就不能算，好，所以我们的 focus 会在这里，OK？ So our focus will be only in here because the stress distribution is so complicated at the top and bottom flanges. Okay, so actually where we can focus is only this part. Okay. Only this part. And this is tau minima. Tau minima. And this is tau maxima. Okay? So you see that this value is no longer 0 because it is not reached to the top and bottom. Okay? So it should be tau maxima and tau minima. The tau minima is not 0 because it still has something up at the top or at the bottom. So it is not 0. Okay? And luckily, because our shear formula can suitable for the rectangle here, okay? So we still can determine the EF, stress in the at the EF. However, if EF go up to the web, we cannot do that, okay? 所以我的意思是说啊，哈，好险，中间还是有我们的长方形的形状，我们还是可以算。但是如果今天这个 EF 跑到翼板上的话，哎，那就不行啦，哈，那就不行，因为它太复杂了。So our focus is only at the column part, okay, the web part. So now let's determine its Q here. Okay, so our Q here is okay, we do that. So okay, you see that is the pink. The flange part, pink. The pink is here. Okay? So you see A1 is this one. And this centroid to the Y, to the neutral axis. So you can see, wow, this is H1 over 2. H1 over 2 is the height of the bottom of the web. Okay? And the rest of this one is the total height minus this part. So it's just the thickness of the web. This is thickness of the web divided by 2. So it's tiny distance plus H1. Okay, so this is the web centroid to the distance of to the neutral axis. So pink. And this is A1, it's just this one. All right. And A2, we can draw about, wow, looks the same.哇，颜色有点打架了。Okay, sorry. May I just change your color? Delete that. Can we do this? Okay. A2. Okay, so A2 here, small one. Okay, and this is Y1. And H1 over 2 minus Y1. So it's just the height of this green part and divide by 2. So divide by 2 and plus Y1. So this is the centroid to the neutral axis. Okay, so after that, Q equal to this. So basically it's still the same, okay? We want to determine the shear stress at this level, and we determine the Q of the upper part of the area. Blah, 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 blah. All right. Next, we are going to determine the I of this I of, what is that? Moment of inertia for this I shape. Okay, this is a little bit difficult, so you need to be you need to be with me. Okay, we have two solutions. The first solution, solution one. Okay, solution one is we can determine that this two yellow region is empty, and this whole region is a bigger one. So you see the height, this is B, and this is H1, right? H1. Okay, and this is T thickness. Okay, so you see this pink, blue here. BX3 divided by 12, no problem, easy, right? And minus yellow part, B minus T, so it should be 2 yellow part times HI3 divided by 12. So it's easier. I become this. Okay, so this is easier to determine the I shape. I of I shape. Okay. Or you can have the second solution. It's relatively difficult, but I encourage you to do that. To practice, to use parallel axis theorem. How can we do that?真丑。Okay, so solution two is that I encourage you to go back home to practice parallel axis theorem. You can do that. Firstly, your red part is okay. You can determine your red part by using BH3 divided by 12. Okay, red part is okay, easy. But you need to determine this upper part, BH3 divided by 12. But you need to move parallelly by using parallel axis theorem. You need to move this axis to the neutral axis and do the second one. And you will get exactly the same value of this. OK， 好，这边讲的就是用大的面积去减掉空的面积，这比较简单。但是呢，你也可以使用 parallel， 你可以回去试试看，中间那个它已经你就直接使用 BH3次方就可以，除以12就可以了，这没有问题。但是上面的话，你还是可以使用 BH3次方除以12，但是你要移动到 neutral axis， 下面也是啊。那这三个加起来的 i， 你应该会等于这个东西 ，OK？ 所以这个 i 是很重要，就是蛮难算的。OK， so if you have any question, just come here and thank you. I will see you next week. 啊，哦，要上线，对哈，谢谢你，那我们就可以继续上了，每次都这样。Thank you. So let's continue. We have 9 minutes left. So thank you. So tau equal to VQ divided by IT. So we just, yeah, V and Q and I, that's it. So it looks like this. Wow, ugly. Okay. So this value can determine like this. So if you substitute all your H1 over 2 into what? Into Y1, okay? H1 over 2 into Y1, you can get your tau minimum, but not 0, okay? Not 0. So this parabola can draw the curve like this, okay? 好，就我们就把刚刚的 Q 啊、I 啊带到这个公式里面，你就会写出一个这个很丑的式子。这很丑的式子，如果你今天去用去代入它，然后算出来的话，你会画出这一条线。好，那这一条线它的左边极值就不会是0了。你可以把这个2分之 H1 带进去，然后你就可以得到这边的 tau min 是多少。OK？ Right, so it's kind of getting more difficult and more difficult. This is the most difficult part in chapter 5. All right, so yeah, almost there, almost there. So, any questions? 听得懂吗？听得懂吗？有点难，有点难。有没有什么问题？可以问吗？就是会不会太复杂？有需要我在哪里再讲一次吗？还好，哦，很棒。哦，我觉得这边是最难的部分了哈，就是全部材料力学里面，我觉得这边这部分就是最难的，因为它实在太复杂了。你要算 Q， 要算 I， 然后你的 Q 又形状很奇怪，然后I 的话又不能如果今天你是用左边的方法的话，大家的轴都维持在直心，正好就在中间的直心，就很棒，很简单。但如果你没有想到要这样算，哦，你下面那个这边的直心是 OK 的，是就对在这里，但是上面的直心你要把它移下来，哇，你要算好多东西，所以这实在是太复杂了。好，那你知道等一下的题目还会有梯形的，梯形的，那这样就很麻烦啊。好了，加油。Okay, so let's continue to examine this one. Again, I said we will determine this one. We will determine this one by using this parabola. Okay, so copy. Next one. Hey. Okay, so here, this is the I shape, and the tau looks like this. And after we do the after we substitute y equal to 0 here, and you can get tau max. And if you substitute y1 positive 1 minus h1 over 2, substitute here, and you can get tau minimum. All right, that's it. And you need to be careful. This is maximum shear stress of the web and minimum shear stress of the web. Okay, of the web, only this web, not for flanges. Okay, not for the top and bottom plate of the web. Okay, then we can determine, because we can determine the shear stress in the web, we can also determine shear force in the web. Okay, shear force in the web, because all we need to do is determine this and times its area. Okay, so if we get the area, we can get the times the area, we can get the shear force. So you see, there are two parts, rectangular part and the parabola part. Okay, rectangle part is V1. V1 equal to tau minimum. Of course, this is tau minimum. Tau minimum. Okay, and this is H1, right? So tau minimum times H1 and times T, the thickness of the web. So this is tau minima, is the shear stress. This is the area, right? So area, and this is shear stress. So this is shear force. Shear force 1. This is for rectangular part. And then the next one is, again, H1. And this part, okay, is called tau max minus tau minima. The tiny thickness. Okay, so this is area again. H1 times T, again, this is the area. And tau maxima minus tau minima is the shear stress, right? And this is really interesting. Okay, here you just minus it, and this is parabola. It is cut through the tangential to the rectangular. Okay, so when you have a circle in the rectangle, your ratio will be 2/3. Do you know this? 如果你有一个方形，然后里面有一个切圆，然后你的切圆的那个面积会是2/3。那为什么会这样呢？ 应该也是从那个 calculus 来的，就是微积分来的。那你 Google 也可以 Google 得到哦。那就这样，你可以试试看，回去算算看，2/3。OK， so this ratio is the area percentage of all these rectangle. Okay, 2/3, 2/3. So this part is 1/3. Okay, this part is 1/3, and this part is 2/3 of the rectangle area shape. Okay, so 2/3. So you sum up y1 and y2, and you can get v web is blah 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 blah. Okay. Well, it's not really it's not really important, but it's just a concept that if you have the shear stress and just time the the you just time the area and you can get a shear force. All right, so 10 o'clock. I guess I need to finish today. And thank you. And this is the most difficult part. And after this shape, next week I will finish this and the most difficult one and most important example. All right. So see you next week. Thank you.